Imagine looking up at the night sky and seeing a blazing streak of light, a fireball racing toward Earth. Did you know that tiny fragments from distant asteroids and planets are constantly falling around us? These are meteorites, pieces of the cosmos that carry secrets billions of years old. From shaping our planet to hinting at the origins of life, each one tells a story that's both ancient and thrilling. Join me as we uncover 100 fascinating facts about meteorites and cosmic impacts. A journey through space, time, and discovery. Fact 1. What meteorites are. Rocks from space that reach Earth. Imagine stepping outside one night and watching a streak of light race across the sky. Most people call it a shooting star, Sess, but in reality it's something far more extraordinary. That flash of light is a tiny visitor from space, burning through our atmosphere at tens of thousands of kilometers per hour, and sometimes a piece of it survives the fiery descent and lands on Earth. That survivor is what we call a meteorite. Meteorites are time capsules, fragments from the earliest days of our solar system, older than any rock found on our planet. They come from asteroids, the Moon, and even Mars, drifting silently through space for billions of years before gravity pulls them down to Earth. When they hit the atmosphere, the friction turns their outer layer molten, creating that bright trail we see. But if they're lucky, or tough, enough to make it to the ground, they become the real treasures scientists and collectors hunt for. What makes them so special isn't just their age, it's what they carry inside. Metals, minerals, and sometimes even traces of water and organic molecules. Each meteorite tells a story about where it came from. Some are full of shimmering iron and nickel, others are stony with glassy grains and tiny crystals. When you hold one, you're literally touching a piece of the cosmos, something that once drifted between the planets before finding its way into your hand. Meteorites are also surprisingly common. Every single day, Earth is struck by tons of space material, most of it tiny dust that burns up before reaching the ground. But every now and then something big survives. A single meteorite fall can light up the sky, shake windows, and leave scientists scrambling to find the fragments before they disappear into soil, water, or collectors' pockets. So next time you see a shooting star, just think, one of those glowing trails could be a messenger from another world quietly making its way to our own. Fact 2. Difference between meteoroids, meteors, and meteorites. It's easy to mix them up. Meteoroid, meteor, meteorite. They all sound almost the same, but they describe 3 stages of one incredible journey. Picture this. Floating in space, a small chunk of rock or metal orbits the sun. That's a meteoroid, a tiny wanderer left over from the creation of planets. They can be as small as grains of sand or as large as boulders. When one of those meteoroids crosses Earth's path and plunges into the atmosphere, friction heats it up. It glows, streaks across the sky, and becomes what we call a meteor, the beautiful shooting star we love to watch during meteor showers. Now, if that glowing traveller survives the intense heat and pressure, and a piece actually reaches the ground, that's when it earns its final name, meteorite. Only a small fraction make it through. Most burn up completely before touching Earth's surface. It's like a cosmic game of survival. Meteoroid, the traveller. Meteor, the fireball. Meteorite, the survivor. And just to make it more interesting, if you've ever held a meteorite in your hand, you've held something older than any rock on Earth. That tiny piece of metal or stone has travelled millions, even billions of years just to end up here. The difference between those 3 words isn't just technical. It's the story of an epic cosmic journey. Fact 3. How meteorites form in space. Long before they ever fall through our sky, meteorites begin their story inside larger bodies, asteroids orbiting quietly between Mars and Jupiter. Billions of years ago, when the solar system was still forming, dust and gas clumped together under gravity. Those clumps grew into planetesimals, the building blocks of planets. Inside those young worlds, heat melted rock and metal, separating them into layers, iron cores, rocky mantles and crusts. Over time, collisions shattered them apart, sending fragments drifting into space. Those fragments cooled, hardened, and became the meteorites we find today. Some formed from molten metal deep inside, becoming solid chunks of iron and nickel. Others formed from rock and silicate minerals, stony meteorites that still carry tiny droplets of glassy material from the solar system's earliest moments. There are even rare types that mix both, shimmering stones with crystal green olivine floating in metallic webs. Each impact, each collision, reshaped their story. They were melted, cracked, and sometimes fused with other fragments. Some even hold microscopic bubbles or minerals that show signs of ancient water. Hints that even back then, the ingredients for life were already moving through space. So when a meteorite lands on Earth, it isn't just a rock. It's the remnant of a time when everything, planets, moons, even Earth itself, was still being born. Fact 4. The journey from asteroid to meteorite. Imagine a lonely asteroid drifting in the darkness, orbiting the sun for millions of years. One day, a violent collision shatters it. A small fragment breaks loose and starts a long, slow fall toward Earth. For ages, it floats silently until gravity catches it. As it enters Earth's atmosphere, it begins to glow. The air compresses and heats up around it, creating that bright streak we call a meteor. Most pieces burn up completely, turning into dust, but some are large or dense enough to survive the fiery plunge. When that fragment finally hits the ground, it's scarred, blackened, and transformed. A meteorite. It might land in a frozen desert, a quiet forest, or the middle of someone's backyard. And while the journey may have lasted millions of years, its final descent happens in seconds. Every meteorite's path is unique. Some start from the asteroid belt, some are knocked free by impacts on Mars or the Moon, and each one carries the memory of that long voyage, from the moment it was born in a collision to the moment it thudded into our world. That small rock travelled across the void and somehow found us. Fact 5. How scientists classify meteorites. When a meteorite lands, the first thing scientists want to know is, what kind is it? Because not all meteorites are the same. They start by looking at composition. The simplest division is into stony, iron and stony iron meteorites. Stony ones are made mostly of silicate minerals. They look like dull grey or brown rocks, but often contain tiny round grains called chondrules. Iron meteorites, on the other hand, are metallic and heavy, with a surface that shines when polished. They're usually fragments from the cores of long-vanished asteroids. Then there are stony iron meteorites, rare hybrids that sparkle with greenish crystals of olivine embedded in metal. Scientists go deeper, classifying them by structure, mineral makeup, and even isotopic signatures, chemical fingerprints that tell where they came from. Some meteorites formed in molten interiors of asteroids. Others are untouched relics from the dawn of the solar system. Each category helps piece together a different part of cosmic history. By studying them, researchers can trace how planets formed, melted, and evolved. In a way, classification isn't just sorting rocks. It's decoding the solar system's family tree. So when a new meteorite is found, it's not just another stone from space. It's a fresh clue, a chapter in the never-ending story of how our cosmic neighbourhood came to be. Fact 6. Stony versus iron meteorites. When you hear the word meteorite, you might picture a single type of rock, something heavy, dark and mysterious. But not all meteorites are the same. In fact, the universe seems to have its own way of sorting them into two main families, stony and iron. Stony meteorites are the most common. About 95% of all those that fall to Earth belong to this group. At first glance, they might look like ordinary Earth rocks, but look closer, and you'll see tiny shimmering grains, sometimes circular glassy droplets called chondrules. These are among the oldest materials in the solar system, older than any mountain, older than any ocean. Each one carries within it the story of how dust turned into worlds. Iron meteorites, on the other hand, are something else entirely. They're dense, heavy, and metallic. So heavy, in fact, that even a small one feels strangely solid in your hand. When polished, their interiors reveal intricate, crisscrossing lines called the Widmanstetten pattern, a natural design formed as iron and nickel cooled in space over millions of years. It's nature's own geometry, frozen in metal. What's fascinating is what they tell us. Stony meteorites come from the crusts of ancient bodies, while iron ones are thought to be the exposed cores of shattered asteroids. Together, they tell a story of destruction and creation, of collisions that broke planets apart and sent fragments drifting across the cosmos, only for some to land quietly on our world. So next time you see a meteorite in a museum, look closer. Whether it's a stony piece of cosmic dust or a metallic shard from an asteroid's heart, you're looking at the building blocks of planets. Fact 7. Stony iron, palisite, meteorites, and their beauty. If meteorites were jewellery, palisites would be the crown jewels. Imagine a stone so mesmerising that it looks like stained glass. Greenish crystals floating in a shiny metallic web. That's what a stony iron meteorite is. Palisites are rare, less than 2% of all meteorites. They formed in a very special place, the boundary between the rocky mantle and the metallic core of a once larger body. In that place, molten metal met crystal rock, creating a fusion of opposites. The result? A stone filled with gem-like olivine crystals, some so transparent that light shines right through them, all suspended in iron nickel. Scientists believe palisites give us a direct look into the interiors of small planetary bodies that broke apart billions of years ago. But beyond the science, there's something poetic about them. When cut and polished, a palisite glows, not just with beauty, but with the memory of cosmic chaos. Collectors treasure them, researchers study them, and anyone who's ever seen one up close never forgets it. It's like holding a fragment of both fire and earth, a frozen meeting point of metal and crystal, born from the universe's most violent collisions. Fact 8. The fusion crust. Formed during atmospheric entry. When a meteorite falls through the atmosphere, it's like a space traveller entering a furnace. As it plummets toward Earth, the air in front of it compresses violently, heating up to thousands of degrees. That heat doesn't just burn the air, it melts the meteorite's surface. But here's where it gets interesting. Even though the outer layer melts, it cools almost instantly once it slows down. The result is a thin, dark coating called a fusion crust, a kind of protective shell that covers the meteorite. It's usually smooth, sometimes glossy, and often dark brown or black. You can even see tiny flow lines or thumbprint-like textures where molten material cooled unevenly. For scientists, the fusion crust is a clue. It tells them that the rock really came from space, not just from a mountain somewhere. It also helps distinguish fresh falls from older finds, because over time, weather and oxidation dull that once dark surface. In a way, the fusion crust is like a meteorite's battle scar, the mark it carries from its fiery descent through the atmosphere. It's proof that the rock survived one of the harshest transitions in nature, from the cold silence of space to the burning rush of Earth's sky. Fact 9. How fast meteorites travel through space. When a meteorite enters our atmosphere, it's not casually drifting along, it's moving at cosmic speed. Most meteoroids travel between 11 and 70 kilometers per second. That's faster than a bullet, faster than sound, faster than anything we experience on Earth. Think about it. At that speed, a small pebble could release as much energy as a hand grenade. Larger ones, They can rival small nuclear explosions. That's why even small impacts can cause such dramatic events. Bright fireballs, sonic booms, and sometimes even shock waves strong enough to break windows. Out in space, there's almost no resistance, so meteoroids can move effortlessly, guided only by gravity. Once they fall toward Earth, though, air resistance slows them dramatically. Most lose over 90% of their speed before they hit the ground. By the time they land, they're often moving at only a few hundred kilometers per hour, still fast but survivable. Their incredible speed isn't just a thrill for skywatchers, it's also a clue to where they came from. Different speeds and trajectories help scientists trace whether they originated from comets, asteroids, or even other planets. So the next time you see a shooting star, remember, that tiny light you see might be racing through the atmosphere faster than your mind can even imagine. Fact 10. The heat and light of atmospheric entry. When a meteorite blazes across the sky, it's one of nature's most dazzling shows. A streak of light so bright it can outshine the stars for a few seconds. But what actually causes that fiery glow? It isn't the rock itself burning up, it's the air. As a meteoroid slams into Earth's atmosphere, the air in front of it is compressed so violently that it heats up to thousands of degrees. That superheated air causes the surface of the rock to melt and vaporize, creating a glowing plasma trail behind it. The colors you see, white, green, orange, come from different elements vaporizing at different temperatures. For the meteoroid, it's a brutal few seconds. The outer layer peels away in molten droplets, creating that smooth, blackened fusion crust. Some fragments explode mid-air as the pressure builds too high. Others survive, smaller but intact, eventually landing as meteorites. It's a fiery entrance, a cosmic flare marking the arrival of something ancient. What begins as a silent traveller in the cold of space ends as a brilliant flash across our sky, reminding us that even in darkness, the universe finds spectacular ways to announce itself. Fact 11. Common minerals found in meteorites. If you were to crack open a meteorite, you'd find a world of shimmering metals and glassy minerals that look nothing like most Earth rocks. These aren't random mixtures. They're the same materials that once swirled in the young solar system, frozen in time. The most common minerals you'd spot are olivine and pyroxene, both made of silicate, the same family that makes up much of Earth's mantle. But in meteorites, they often appear as tiny crystals, locked together in patterns that haven't changed for billions of years. Then there's plagioclase, a feldspar mineral that adds a faint sparkle when polished. In metallic meteorites you'd find kamacite and taenite, both rich in iron and nickel. These two form those stunning geometric patterns that appear when the metal is etched, patterns that no human hand could ever forge. And here's the wild part. Some meteorites also contain rare minerals that don't exist naturally on Earth. Under the intense heat and pressure of space collisions, they create new compounds never seen before. A single meteorite might hold dozens of tiny unnamed minerals, each one offering a new clue about conditions deep in ancient asteroids. So, when scientists study meteorites, they're not just looking at rocks, they're looking at the raw ingredients of planets, preserved perfectly since the dawn of our solar system. Fact 12. Nickel-iron alloys and magnetic properties. Pick up an iron meteorite, and you'll notice something right away. It feels heavier than it looks. That's because it's packed with nickel-iron alloys, dense metals that formed deep inside ancient asteroids. These alloys, mainly kamacite and taenite, cooled so slowly over millions of years that they grew intricate interlocking patterns, like nature's own fingerprint. And here's the fun part. Iron meteorites are magnetic. If you hold a magnet near one, it'll cling instantly. That magnetism comes from the same metallic core materials that once helped planets like Earth generate their magnetic fields. In fact, these meteorites are believed to be fragments of the cores of long-destroyed planetesimals. early building blocks of planets that collided and broke apart. Their magnetic strength also helps scientists identify meteorites in the field. Many meteorite hunters carry small magnets, knowing that even beneath sand or soil, the faint pull of cosmic metal might reveal something extraordinary. Beyond science, there's a certain awe in holding one. It's heavy, cold, and ancient, a solid piece of space iron that once drifted between worlds before finding its final resting place here. Fact 13. Chondrules, tiny molten spheres. Inside chondrites, imagine holding a rock filled with tiny glassy beads, each one a frozen droplet from the birth of the solar system. Those little spheres are called chondrules, and they're one of the most fascinating features in meteorites. Chondrules formed over 4.5 billion years ago when dust and gas were swirling around the newborn sun. For a brief, mysterious moment, that dust was flash-heated, maybe by shock waves, maybe by lightning-like discharges, and melted into glowing droplets. As they cooled, they solidified into tiny spheres, usually less than 1 millimeter across. Over time, these spheres clumped together, eventually becoming the first solid building blocks of asteroids, and later, planets. Meteorites that contain chondrules are called chondrites, and they're the most primitive materials we can touch. They've barely changed since those early days, still carrying traces of that original cosmic fire. When scientists study chondrules, they're peering directly into the past, a time before Earth existed, before any life, before any oceans or continents. Each one is a tiny relic of creation, locked inside a stone that fell from the stars. Fact 14. Carbonaceous chondrites and organic compounds. Among all meteorites, few are as mysterious or as precious as carbonaceous chondrites. These dark, crumbly stones look unimpressive at first glance, but they hide something extraordinary: the chemical fingerprints of life's ingredients. These meteorites are packed with carbon-rich compounds, amino acids, hydrocarbons, and even traces of water trapped in their minerals. They're like tiny laboratories that record what was floating through space before planets formed. Some scientists believe they could have delivered those organic molecules to early Earth, seeding the chemistry that later led to life. The Murchison meteorite, which fell in Australia in 1969, became famous for this very reason. It contained over 70 different amino acids, far more than what's typically found in living organisms on Earth. Each one formed naturally in space, without any biology involved. Carbonaceous chondrites are also some of the oldest and least altered materials known. They carry within them the story of how the solar system began, a mixture of dust, ice, and organic molecules that once floated freely between the stars. When you hold one, you're holding not just a rock, but a record of chemistry that might connect us to the origins of life itself. Fact 15. Rare achondrites, fragments of other worlds. Most meteorites are primitive, untouched since the dawn of time. But achondrites are different. They've been melted, reshaped, and sometimes even part of volcanic worlds before being blasted into space. In short, achondrites are fragments of other planets. Some achondrites come from the moon, thrown off by meteor impacts that ejected pieces of lunar rock into orbit before they eventually landed on Earth. Others come from Mars. We know because the gases trapped inside their minerals match the Martian atmosphere measured by spacecraft. These stones tell us that the same forces shaping our planet, heat, lava flows, volcanic eruptions, were also at work elsewhere in the solar system. Holding an achondrite is like holding a piece of another world's crust, a sample from a place no human has ever stood. They're rare, and each one is precious. Some even show traces of ancient volcanic activity, with minerals crystallized from molten rock. Others carry microscopic bubbles of gas, tiny sealed messages from the surface of another planet. When scientists study achondrites, they're not just examining meteorites, they're exploring the geology of worlds far beyond our reach, and every new fragment that falls to Earth expands our map of the cosmos, one rock at a time. Fact 16. Pallasites and olivine crystals. If meteorites were jewellery, pallasites would be the crown centrepiece. They're so striking that even people who know nothing about space stop and stare. Picture a slice of metal filled with golden green crystals that glow when light passes through them. That's a pallasite, a stony iron meteorite born in a place where fire and metal met billions of years ago. Pallasites form deep inside large asteroids, right at the boundary between the metallic core and the rocky mantle. It's the kind of region where molten metal mixes with solid minerals, creating something both chaotic and breathtaking. The green crystals you see are olivine, a silicate mineral also found on Earth. It's the same material that, in gem form, is called peridot. But in a pallasite, those olivine crystals are suspended inside a shining matrix of nickel iron, like stars trapped in molten gold. What makes pallasites even more fascinating is their rarity. They make up less than 2% of all meteorites, yet they give scientists a direct glimpse into the internal structure of early planetesimals, the building blocks of planets. When you hold one, you're literally holding a fragment from a boundary layer that existed before Earth was fully formed. Every pallasite slice tells two stories at once, one of destruction, from the collision that tore a body apart, and one of creation, from the incredible beauty that chaos left behind. Fact 17. Isotopic fingerprints that tell their origins. Every meteorite has a hidden signature, not in its colour or texture, but in its atoms. Scientists call it an isotopic fingerprint, and it's how they trace where a meteorite came from. You see, not all atoms of an element are identical. Some have slightly different masses, called isotopes. The ratios between these isotopes vary depending on where the material formed in the solar system. For example, oxygen, chromium and titanium isotopes in a meteorite can tell researchers whether it originated from Mars, the Moon, or an asteroid. It's like cosmic forensics. When a new meteorite is discovered, scientists analyse its isotopic composition in laboratories. The results can pinpoint its birthplace, sometimes even identifying which specific asteroid it came from. That's how we know certain meteorites were ejected from Mars, or that others came from the Vesta asteroid. These fingerprints also help reconstruct the timeline of our solar system's formation. Isotopic differences reveal which materials formed closer to the Sun, which ones condensed in colder regions, and how those materials later mixed. So even though meteorites may look like random stones, their isotopic patterns act like ancient passports, records stamped by the environments they were born in, carrying their origins across billions of years and millions of miles. Fact 18. Micrometeorites. Tiny cosmic dust. Everywhere. You might not realise it, but space dust is falling all around you, right now. Every day, Earth collects tens of thousands of tons of micrometeorites, tiny grains of cosmic material that drift through the atmosphere like invisible visitors. Each one is smaller than a grain of sand, but together they're a constant reminder that we live in an open system, a planet being sprinkled by the universe. These particles come from comets, asteroids, and even the tails of meteor streams. When they enter the atmosphere, they move fast enough to heat up and briefly glow, but because they're so small, they cool down quickly and survive the journey intact. Scientists find micrometeorites everywhere, trapped in polar ice, collected from rooftops, and even embedded in deep-sea sediments. Under a microscope, they're beautiful, tiny metallic spheres, smooth, shiny, and often magnetic. Each one is a miniature meteorite, carrying minerals and metals older than Earth's continents. Studying them helps scientists understand the constant flow of material from space to Earth. Some even contain traces of complex carbon molecules, showing that organic chemistry isn't confined to big space rocks. It's part of the cosmic dust that falls on us daily. So next time you wipe off some dust, remember, A tiny fraction of it might have come from the stars. Fact 19. Tektites. Glass formed from ancient impacts. Imagine the ground turning to liquid glass in a split second. That's what happens when a large meteorite strikes Earth. The intense heat and pressure melt the surrounding rock and soil, flinging it into the air. As it cools mid-flight, that molten material solidifies into strange glassy droplets called tektites. Tektites are not meteorites. They're Earth's own rocks, transformed by the violence of impact. They're usually black or dark green, lightweight and smooth, often shaped like buttons, teardrops, or discs. You can find them scattered across vast regions known as strewn fields, such as those in Southeast Asia, Central Europe, and parts of North America. Their chemical composition matches terrestrial rocks, but their structure tells a story of extreme heat. Temperatures so high that everything melted and then cooled within seconds. Some tektites even contain tiny bubbles or streaks of silica, frozen mid-splash. For scientists, tektites are like time capsules of catastrophic events. They record not only the impact itself, but also how Earth's crust responded, and for collectors, they're among the most fascinating natural glasses ever created, born in fire, flung across continents, and polished by time. When you hold a tektite, you're holding the aftermath of an explosion so powerful it changed the landscape, a fragment of Earth's memory, born from a moment of cosmic violence. Fact 20. Shock metamorphism. How impacts alter rock. When a meteorite slams into Earth, it releases energy beyond comprehension, enough to melt, vaporize, or even rearrange the atomic structure of the ground it hits. This process is called shock metamorphism, and it leaves behind some of the most dramatic signatures in geology. Under that immense pressure, sometimes millions of times higher than normal atmospheric pressure, solid rock behaves like a fluid for an instant. Crystals deform, minerals melt and recrystallize, and new structures form that can only exist under such extreme conditions. Quartz, for example, can transform into high-pressure forms like coesite or stishovite, minerals that only appear in impact sites or deep inside planets. Rocks near the impact may show shatter cones, cone-shaped fractures that radiate out from a single point, like frozen shock waves. Microscopic features, such as planar deformation lines, mark the spots where mineral lattices were rearranged in an instant of unimaginable force. Shock metamorphism doesn't just reshape rocks. It's a geological signature of cosmic violence. It's how scientists identify ancient craters, even when erosion or vegetation has hidden their outlines. Every crater tells a story written in these altered minerals, a story of a moment when the calm surface of Earth met something far greater than itself, and for a heartbeat, everything changed. Fact 21. Meteorites from the asteroid belt. Most meteorites that land on Earth began their lives far away, drifting in the vast region between Mars and Jupiter, known as the asteroid belt. It's a place filled with countless rocky bodies, leftovers from the dawn of the solar system. While it might sound crowded, space out there is so vast that these asteroids are separated by enormous distances. Yet, every now and then, collisions happen, and that's where the story of most meteorites begins. When two asteroids collide, fragments break off and start new journeys through space. Some of these pieces are thrown out of the belt entirely, falling into orbits that cross Earth's path. Over time, sometimes millions of years later, gravity brings them home to us as meteorites. These space rocks carry the same ingredients that once formed the planets: silicates, metals, and traces of organic material. In fact, the chondrites, one of the most common types of meteorites, come directly from these primitive asteroids. They've remained almost unchanged since the solar system's earliest days. Holding a meteorite from the asteroid belt is like holding an untouched page from the beginning of planetary history, material that has waited billions of years to tell its story, finally landing here by chance. Fact 22. Lunar meteorites. Pieces of the moon on Earth. Imagine walking across a desert, spotting a strange rock, and realizing it came from the moon. It's not science fiction, it's real. Lunar meteorites are fragments of the moon that were blasted off its surface by ancient impacts, then drifted through space before landing on Earth. No spacecraft brought them here. Instead, meteor impacts on the moon were powerful enough to eject debris beyond lunar gravity. Those fragments wandered for thousands or even millions of years before Earth's gravity pulled them in. Scientists can tell a rock is lunar by analysing its mineral composition and isotopic ratios. They match perfectly with the samples brought back by astronauts. Lunar meteorites are usually made of basalt or anorthosite, the same materials that form the moon's surface. Some even show tiny glassy bubbles, evidence of exposure to the harsh vacuum of space. These meteorites give researchers valuable insight into parts of the moon never sampled directly. Some come from the far side, areas untouched by human exploration. Each one adds to the puzzle of a lunar history, a story of impacts, volcanic flows, and time frozen in silence. So yes, it's entirely possible that a piece of the moon could be sitting quietly in a museum, or even in someone's rock collection, waiting to remind us how close the heavens can come to home. Fact 23. Martian meteorites. Clues to Mars' past. Few discoveries spark as much excitement as finding a Martian meteorite. These rare stones come from Mars itself, fragments launched into space by colossal impacts that broke the planet's crust and hurled debris across millions of kilometers. How do we know they're from Mars? Their gases match the Martian atmosphere exactly. Scientists compared the trapped gases inside these meteorites to the measurements taken by Mars landers, and the match was perfect. That's how we know these pieces really came from the red planet. Martian meteorites, known as SNC meteorites, Chagotites, Naclites, and Chassonites, reveal a lot about Mars's history. They tell us the planet was once volcanically active, with magma flows and possibly liquid water. Some contain minerals that formed in watery environments, suggesting that Mars once had conditions suitable for life. Each fragment that reaches Earth is a time capsule from another world. Holding one is like holding a piece of Mars' ancient surface, shaped by dust storms and silence. It's humbling to think that a rock could travel across space for millions of years, then land here just to whisper what Mars was like long before we ever saw it up close. Fact 24. Possible meteorites from Mercury or Vesta. Most meteorites come from the asteroid belt, and some from the Moon or Mars, but a few might have even stranger origins. Scientists suspect that some meteorites could come from Mercury or the asteroid Vesta, offering rare glimpses into two very different kinds of worlds. Mercury meteorites would be extremely rare because it's so close to the Sun. For a rock to escape Mercury's gravity and not fall into the Sun is a near impossible journey. But researchers have found a few meteorites whose chemistry, rich in certain metals and depleted in volatiles, matches what we'd expect from Mercury's surface. Vesta, on the other hand, is a confirmed source. The head meteorites, Howardites, Eucrites, and Diogenites are believed to come from Vesta. The evidence comes from spacecraft observations showing identical spectral patterns between those meteorites and the asteroid itself. These meteorites help scientists understand how planetary crusts form and evolve. Each world leaves a unique mark on its rocks, a fingerprint in minerals, isotopes, and structure. And when one of those fragments makes its way here, it adds another voice to the cosmic story of how diverse and dynamic our solar neighbourhood really is. Fact 25. How we know where a meteorite came from. Every meteorite has a past, and scientists have developed clever ways to uncover it. To figure out where a meteorite came from, researchers rely on a mix of chemistry, isotopes, texture, and sometimes even trapped gases. First, they look at composition. Certain elements or minerals reveal the type of body it formed on. For example, basaltic meteorites likely came from volcanic planets or asteroids with molten interiors. Then come isotopic ratios, especially of oxygen, chromium and titanium. These ratios act like cosmic DNA, helping pinpoint whether a rock originated from Mars, the Moon, or an asteroid. In some cases, gases trapped inside a meteorite provide direct proof. Martian meteorites, for example, contain tiny bubbles with the exact same mix of gases found in Mars' atmosphere. Finally, orbit tracking can occasionally connect a meteorite to a known parent body. When a meteor is seen entering Earth's atmosphere and its fall is tracked precisely, scientists can calculate its orbit backward, sometimes linking it to a specific asteroid. It's a bit like detective work across time and space. Every meteorite is a clue, every isotope a fingerprint, every fracture a line in a cosmic diary. And when all those clues come together, we can trace a rock's journey from the heart of an asteroid or the crust of a distant planet, all the way to the palm of a human hand. Fact 26. The oldest meteorites, older than Earth's surface. Imagine holding a rock that's older than the Earth's crust, something that formed before our planet even had oceans or continents. That's what happens when you hold one of the oldest meteorites ever found. These ancient stones date back over 4.5 billion years, making them true time travelers from the earliest days of the solar system. Most of these meteorites, particularly the chondrites, are fragments of primitive asteroids that have remained mostly unchanged since they first formed. While Earth's surface has been reshaped countless times by volcanoes, erosion, and tectonic activity, these meteorites stayed frozen in space, untouched by all that chaos. When they finally land here, scientists study their age using radiometric dating, measuring isotopes of uranium, lead, and other elements to track how long ago they solidified. The results are astonishing. Some meteorites formed only a few million years after the sun itself ignited. These ancient rocks are like fossils of the universe, silent witnesses to the birth of everything familiar. They tell us that before Earth's mountains rose or its seas formed, there were already pieces of solid matter drifting through the darkness, waiting for gravity to bring them together into something new. Fact 27. Primitive meteorites, preserving solar system history. Not all meteorites are created equal. Some are primitive, meaning they've barely changed since the solar system's earliest moments. These rare visitors act like sealed containers of cosmic history, preserving the original ingredients that built planets. Primitive meteorites, especially the carbonaceous chondrites, contain materials that condensed from the solar nebula, the giant cloud of gas and dust that surrounded the newborn sun. Inside them are minerals, tiny chondrules, and sometimes even pre-solar grains, dust particles older than the sun itself. These meteorites haven't been melted or altered by geological processes, which means they still carry the chemical signatures of the solar system's raw beginnings. By studying them, scientists can reconstruct what conditions were like when planets were just forming. The temperatures, the chemical makeup, and the presence of volatile compounds. It's almost like having a time capsule that opens a window to the dawn of our solar family. Each primitive meteorite is a tiny archive, holding the blueprint of how gas and dust came together to form worlds. Fact 28. Water-bearing meteorites. When you think of water, you probably picture rivers, rain, or oceans. But some of the earliest water on Earth might have arrived from meteorites. Certain types, especially carbonaceous chondrites, contain minerals that formed in the presence of liquid water. Some even carry small amounts of actual water trapped inside. These meteorites show that asteroids, far from being dry, dusty rocks, once held ice and liquid water in their interiors. Over time, that water reacted with other materials, creating hydrated minerals like clays. When fragments of these asteroids eventually fell to Earth, they brought with them traces of that ancient water. By analysing the hydrogen isotopes in these meteorites, scientists can compare them with Earth's oceans, and remarkably, they're nearly identical. This suggests that much of Earth's water may have come from similar water-rich bodies bombarding the planet during its early history. In other words, those harmless-looking space rocks might have delivered the most essential ingredient for life. Each water-bearing meteorite carries a quiet reminder. The story of Earth's oceans may have begun far from home, written in the ice and stone of a forgotten asteroid. Fact 29. Organic molecules found in space rocks. It sounds like science fiction, but it's true. Meteorites contain organic molecules, the building blocks of life. Scientists have found amino acids, nucleobases, and even complex hydrocarbons in certain meteorites, especially the carbonaceous types. These molecules aren't alive, but they're essential for life as we know it. They formed naturally in space, inside cold molecular clouds, in the solar nebula, or through chemical reactions on asteroids. Protected within rock and ice, they survived the long journey across space and the fiery plunge through Earth's atmosphere. One of the most famous examples is the Murchison meteorite, which fell in Australia in 1969. It contained over 70 different amino acids, far more than are typically found in living organisms on Earth. The discovery proved that organic chemistry isn't unique to our planet. It happens naturally in space, suggesting that the ingredients for life are scattered throughout the universe. These organic-rich meteorites act as cosmic messengers, hinting that the recipe for life might be far more common than we once imagined. Fact 30. Clues. Meteorites. Give about planetary formation. Meteorites are more than just space debris, they're storytellers. Each one carries clues about how planets formed billions of years ago. By examining their chemistry, structure, and isotopes, scientists can piece together how dust and gas in the early solar system turned into solid worlds. Some meteorites show evidence of melting and differentiation, processes where heavier materials sank to form cores, while lighter silicates rose to form crusts. This tells us that small bodies were already forming mini-planets long before Earth existed. Others, like chondrites, record an earlier stage, when dust particles first clumped together into solid rock. Through these stones, we can trace the transition from tiny grains floating in space to full-fledged planets orbiting the Sun. Meteorites even reveal the timing of these events, when certain elements condensed, when heat sources melted their interiors, and when collisions reshaped their structure. In a way, meteorites are like missing pages from a cosmic blueprint, fragments that show how a chaotic cloud of dust and fire became an orderly family of worlds. Every piece that lands on Earth is another puzzle piece in understanding where we came from, and how every planet, including our own, began as nothing more than dust in the dark. Fact 31. What causes shooting stars? You've probably seen one. A sudden streak of light flashing across the night sky, gone in an instant. We call it a shooting star, but of course it's not a star at all. It's a meteor, a tiny piece of cosmic debris burning up as it rushes through Earth's atmosphere. Most of these particles are no bigger than a grain of sand. They travel through space quietly until they collide with Earth at astonishing speeds, sometimes over 70 kilometers per second. When they enter the atmosphere, friction with the air causes them to heat up and glow brightly. The air around them also becomes ionized, producing that sharp, bright streak we see from the ground. Within seconds, the tiny rock vaporizes completely, leaving only a brief trail of light. It's a simple moment, but it connects us directly with the wider universe. Dust from ancient comets and asteroids turned into a flash that anyone can see from their backyard. And every shooting star reminds us that our planet is not alone in space. It's constantly interacting with the remnants of things that once helped shape it. Fact 32. Difference between a meteor and a fireball. All fireballs are meteors, but not all meteors are fireballs. The difference comes down to brightness and size. A typical meteor, what we call a shooting star, is usually caused by a tiny particle burning up high in the atmosphere. But if the object is larger, say the size of a pebble or a rock, it burns much more intensely, producing a bright, long-lasting glow. That's a fireball. Fireballs can sometimes light up the entire sky, even casting shadows on the ground. They often break apart as they travel, leaving glowing trails that linger for several seconds. In some cases, fragments survive the journey and fall to Earth as meteorites. Astronomers track these events using specialized cameras, and eyewitnesses often describe them as dazzling, colorful streaks that turn night into day for a heartbeat. Seeing one feels almost surreal, a brief, brilliant moment when space quite literally falls to Earth. So next time you spot a meteor that's unusually bright or slow-moving, you might just have witnessed a fireball, a cosmic rock putting on its final, spectacular performance. Fact 33. Bolides. When a meteor explodes in the sky. Sometimes a meteor's fiery journey doesn't end quietly. Instead, it ends with a boom. These exploding meteors are called bolides, and they're some of the most dramatic natural events you can witness. As a large meteoroid plunges into the atmosphere, the pressure around it builds rapidly. The outer layers begin to heat, crack, and fragment. Eventually, the stress becomes too great, and the rock explodes mid-air, releasing a burst of energy equivalent to tons of TNT. That explosion produces a brilliant flash that can outshine the moon, and in some cases even create shock waves strong enough to shake buildings or break windows. One of the most famous examples happened over Chelyabinsk, Russia in 2013. The bolide exploded about 30 kilometers above the ground, lighting up the sky and generating a shockwave felt for miles. Bolides remind us how much energy even small space rocks can carry. They're not just visual spectacles, they're raw demonstrations of cosmic power meeting atmospheric resistance. And yet, for all their violence, bolides also bring fragments of space closer to us, scattering meteorites across the ground, quiet relics of an explosive moment in the sky. Fact 34. The sound waves of meteor explosions. It's not just light that meteors produce. It's sound too, though we often don't hear it right away. When a large meteor explodes or breaks apart in the atmosphere, it creates shock waves that move through the air and sometimes even the ground. These waves can produce booming or rumbling noises, much like distant thunder. The sound can arrive minutes after the flash, because light travels faster than sound. In very large events, like the Chelyabinsk explosion, the shockwave can be powerful enough to shatter windows and set off car alarms. Scientists study these low-frequency waves, called infrasound, to measure the energy and altitude of the explosion. Even when a meteor isn't visible, infrasound detectors around the world can pick up its presence, proof that something huge just happened far above us. Occasionally, smaller meteors also produce faint electrophonic sounds, sizzling or crackling noises heard simultaneously with the flash. These might be caused by electromagnetic interactions with nearby objects, like metal fences or hair. So the next time you see a bright meteor streak across the sky, listen closely. Even if the sound arrives late, it's the sky itself reacting to a visitor from beyond. Fact 35. Famous fireball sightings through history. For as long as humans have looked up, we've seen bright streaks of fire in the heavens and recorded them with awe, fear, or fascination. Fireballs have been witnessed throughout history, leaving behind stories that blend wonder with mystery. In 1908, the Tunguska event in Siberia flattened thousands of square kilometers of forest. Though no crater was found, scientists believe a massive meteoroid or comet exploded mid-air, releasing energy hundreds of times greater than an atomic bomb. In more recent memory, the Chelyabinsk fireball of 2013 streaked across the Russian sky, brighter than the sun, and its shockwave injured over 1,000 people. The dashcam footage went viral, showing how suddenly the sky can erupt into light. But these aren't the only ones. Historical records describe fireballs as omens or celestial messages, bright visitors that startled entire cities or lit up oceans. Sailors once saw them over the sea, farmers over their fields, and travellers on quiet nights when the world seemed asleep. Today, we understand the science behind them, but the wonder remains the same. A fireball reminds us how alive the sky truly is, that even on the calmest night, something extraordinary might suddenly blaze into view, turning darkness into daylight for just one unforgettable second. Fact 36. How meteor showers occur. On most nights, you might see a few random meteors streaking across the sky, but sometimes the heavens put on a full performance. That's a meteor shower, when dozens or even hundreds of meteors flash across the sky every hour. But where do they all come from? Meteor showers happen when Earth passes through a trail of debris left by a comet. As a comet travels around the Sun, it sheds dust and small particles along its orbit. These bits remain floating in space, forming a stream. When our planet's orbit crosses that stream, those particles hit Earth's atmosphere at high speed and burn up, producing brilliant streaks of light. What's fascinating is that these meteors are incredibly small, most no bigger than grains of sand. Yet when thousands of them enter the atmosphere at once, the night sky can look alive with motion. Every shower seems to come from a specific point in the sky, called the radiant, which gives the shower its name. For example, the Perseids appear to radiate from the constellation Perseus. Meteor showers are a reminder that Earth isn't standing still. It's moving through a cosmic river of dust and light, a pattern repeated year after year as our planet keeps its steady path around the Sun. Fact 37. The Perseids and Leonids, annual cosmic shows. Every year, skywatchers look forward to two of the most spectacular meteor showers, the Perseids in August and the Leonids in November. They're annual reminders of how predictable, yet magical, the cosmos can be. The Perseids come from debris left behind by Comet Swift-Tuttle. When Earth crosses the comet's trail, hundreds of bright meteors flash through the night sky. The Perseids are known for their consistency. They put on a reliable show, often producing 60 to 100 meteors per hour under dark skies. Warm summer nights make them perfect for lying back and watching with friends. The Leonids, on the other hand, have a reputation for drama. They originate from Comet Tempel-Tuttle and occasionally produce full-blown meteor storms. In 1833 and again in 1866, witnesses described thousands of meteors raining from the sky, so many that people thought the world was ending. Each of these showers has its own rhythm. The Perseids are gentle and frequent, like steady fireworks, while the Leonids are rare bursts of intensity, sudden celestial rainstorms that turn the sky into a glittering river of motion. Together, they remind us that even the emptiness of space is full of rhythm and return, a dance of dust that never quite ends. Fact 38. How comets create meteor streams. Every meteor shower begins with a comet, an icy wanderer leaving a trail of dust and debris as it journeys around the Sun. As sunlight warms a comet's surface, the ice turns to gas, releasing trapped dust grains into space. These grains spread out along the comet's orbit, forming what's called a meteor stream. Over time, that stream stretches and disperses, but it stays roughly in the same path. Each time Earth's orbit intersects it, we experience a meteor shower. The composition of the comet, how dusty or icy it is, determines how rich the meteor stream will be. Some of these streams last for thousands of years. Others fade as solar radiation and gravitational forces scatter the particles. Still, as long as the comet keeps returning, it refreshes its trail with new material. The next time you watch a meteor shower, think of it as the afterglow of a comet's passing, the lingering footprint of something ancient still shaping our sky long after the comet itself has moved on. Fact 39. Why some meteor showers repeat. Yearly. Ever wonder why meteor showers happen around the same time every year? The reason lies in Earth's orbit and the way it crosses the same cosmic debris fields again and again. When a comet leaves its trail of dust, that trail stays in roughly the same place in space, orbiting the Sun just as the comet does. Because Earth travels the same route around the Sun every year, it passes through those debris trails at predictable times. That's why the Perseids always arrive in mid-August, and the Geminids in December. The timing never changes much because both Earth's path and the comet's debris field stay stable over centuries. Each year, the display might vary slightly depending on how dense the stream is, or how the particles have shifted under the influence of planets like Jupiter. But overall, these recurring showers act like cosmic anniversaries, moments when Earth retraces its steps through ancient paths of dust, lighting up the sky in celebration. It's one of the most beautiful rhythms in nature, a planet, a comet, and the memory of their encounter replayed in sparks and light every single year. Fact 40. The largest observed meteor airburst events. Sometimes, a meteor doesn't just burn brightly, it explodes with power rivaling nuclear energy. These are called airbursts, and they're among the most energetic natural events on Earth. The most famous is the Tunguska event of 1908. A huge object, likely a stony meteoroid about 50 meters wide, entered Earth's atmosphere over Siberia and exploded about 10 kilometers above the ground. The blast flattened 80 million trees across 2,000 square kilometers. The shockwave was detected around the world, yet no crater was ever found. The rock completely disintegrated mid-air. More recently, in 2013, the Chelyabinsk meteor exploded high above Russia with the force of several hundred kilotons of TNT. Its shockwave shattered windows across 6 cities and injured over 1,000 people, yet again leaving no crater. Historical records also hint at earlier airbursts, strange flashes, thunders, and waves of heat observed across centuries. Each one is a reminder that space is not empty and peaceful but dynamic, and sometimes dangerous. Even now, scientists monitor the skies constantly, mapping near-Earth objects and studying airbursts to understand their behavior. These events may be rare, but they show us something profound. Earth is still part of an ever-changing system, where the universe occasionally reminds us of its raw, breathtaking power. Fact 41. The Hoba meteorite, world's largest intact piece. Lying quietly in a Namibian field, the Hoba meteorite holds a record no other space rock can match. It's the largest intact meteorite ever found on Earth. Discovered in 1920, this enormous iron mass weighs about 60 tons and has never been moved from where it landed. Hoba is made mostly of iron and nickel, giving it a metallic sheen even after centuries of weathering. Scientists believe it fell around 80,000 years ago, but it hit the ground at a shallow angle and low speed, so it didn't leave a crater. What's most astonishing is how well preserved it is. You can still see the flat surfaces where it partially melted during its descent. Today, Hoba remains exactly where it fell, protected as a national monument. It's not just a meteorite, it's a monument to the immense and ancient power of the cosmos, resting in a quiet corner of Earth. Fact 42. The Sikhote Alin Fall of 1947. On a cold February morning in 1947, the skies over eastern Russia lit up with fire. A massive iron meteorite exploded over the Sikhote Alin mountains, showering the snowy forest with glowing fragments. Witnesses described blinding flashes and thunderous booms as thousands of fiery pieces rained down from the sky. The largest fragments gouged out craters several meters wide. In total, scientists recovered over 20 tons of meteorite material, making Sikhote Alin one of the largest observed meteorite falls in recorded history. Many of the fragments are coated with a distinctive fusion crust, a thin, melted layer formed during atmospheric entry, and their surfaces are pitted with thumbprint-like depressions called regmaglypts. The Sikhote Alin Fall is remarkable not only for its size and violence, but also for its timing. Occurring in the 20th century, it allowed modern scientists to study a major meteorite event in detail, a fiery reminder that space still occasionally touches Earth with dramatic force. Fact 43. The Peekskill meteorite that hit a car. On the evening of October the 9th, 1992, residents of the eastern United States witnessed a dazzling fireball streaking across the night sky. Travelling over 700 kilometres before it fell, the meteor ended its journey in Peekskill, New York, with a spectacular impact. The meteorite, a dense stony type called an H6 chondrite, slammed into a parked 1980 Chevrolet Malibu, crushing its trunk and embedding itself inside. The car's owner, Michelle Knapp, was shocked to find a smoking rock weighing 12 kilograms in the wreckage. What made this event truly unique was that the fireball was captured on video by multiple witnesses at a football game, making it one of the best documented meteorite falls ever recorded. The Peekskill meteorite became an instant celebrity, part of science, part of pop culture. Its fusion of cosmic mystery and earthly coincidence made it a symbol of just how unpredictable the universe can be. Fact 44. The Ensisheim meteorite of 1492. Centuries before telescopes or space science, a loud explosion over the skies of Alsace, France, startled villagers on a November day in 1492. They rushed to find a massive stone embedded deep in a wheat field near the town of Ensisheim. Weighing over 120 kilograms, it became known as the Ensisheim meteorite, the oldest recorded meteorite fall in European history. Locals believed it was a divine sign, and Emperor Maximilian I ordered the stone preserved as a heavenly omen. Over the years, people chipped off pieces as souvenirs, but the main mass still survives today in a museum in Ensisheim. Its survival through the ages marks it as one of humanity's earliest physical connections to the wider cosmos. Proof, centuries before modern science, that stones can indeed fall from the sky. Fact 45. The Chelyabinsk event in 2013. On February 15, 2013, a blinding flash swept across the morning sky over Chelyabinsk, Russia. Moments later, a deafening shockwave shattered windows, set off car alarms, and injured over 1,000 people. The culprit was a 20-metre-wide stony asteroid weighing about 13,000 tons, entering the atmosphere at more than 60,000 kilometres per hour. The explosion released energy equivalent to nearly 30 Hiroshima bombs. Most of the object disintegrated in the air, but fragments rained down across the region, with the largest, a half-ton piece, later recovered from the bottom of Lake Shebakul. The Chelyabinsk event was the largest airburst since Tunguska, and it marked a turning point in global awareness about near-Earth objects. Thanks to modern cameras and sensors, it became one of the most studied meteor events in history, a vivid reminder that Earth's sky, though peaceful, is never entirely safe from cosmic visitors. Fact 46. The Tagish Lake meteorite and organic compounds. It was a cold January morning in 2000 when the sky above Canada's Yukon Territory lit up with a blinding streak of fire. Moments later, chunks of rock rained down onto the frozen surface of Tagish Lake. What looked like a simple fall of space debris turned out to be one of the most scientifically valuable meteorites ever found. The Tagish Lake meteorite is a carbonaceous chondrite, a rare primitive type of meteorite that contains complex organic compounds and even traces of amino acids, the chemical building blocks of life. Because it landed on clean ice and was recovered quickly, the rock remained almost uncontaminated, giving scientists a pristine sample from the early solar system. Inside it, researchers found not just carbon and water-rich minerals, but also microscopic organic molecules formed billions of years ago. These molecules tell a story of chemistry that predates Earth itself, material that may have once swirled in the same cloud of dust that became the planets. The Tagish Lake meteorite is more than just a space rock. It's a frozen message from the dawn of time, quietly whispering how the ingredients for life might have arrived here from the stars. Fact 47. The Allende meteorite, a cosmic time capsule. On a February night in 1969, a brilliant fireball streaked over Mexico and exploded near the village of Allende. Thousands of fragments fell across the desert, creating what scientists would later call the most studied meteorite in history. The Allende meteorite is a type of carbonaceous chondrite filled with calcium-aluminum inclusions, or CAIs, the oldest known solid materials in the solar system. These tiny white specks are over 4.5 billion years old, older than Earth's crust itself. Each fragment of Allende is like a page torn from the universe's diary, recording the early moments of our solar system's birth. Scientists studying it discovered isotopic fingerprints that revealed how the first solids condensed from the solar nebula, the swirling cloud of gas and dust that became the sun and planets. The Allende meteorite is often called a cosmic time capsule for good reason. It carries within it a record of the solar system's earliest chemistry, a physical link to the very beginnings of everything we know. Fact 48. The Campo del Cielo iron masses in Argentina. Long before modern scientists studied meteorites, ancient peoples in Argentina already knew of the Campo del Cielo, field of the sky. Scattered across the plains of Chaco province are massive lumps of iron that fell thousands of years ago from a colossal meteorite impact. These iron masses, some weighing up to 50 tons, are part of a huge strewn field stretching over several kilometers. The meteorite broke apart before hitting the ground, leaving behind numerous craters and metallic fragments that indigenous communities used for tools and trade long before Europeans arrived. Campo del Cielo is mostly composed of iron and nickel, its metallic surface etched with the famous Widmanstätten patterns, crisscrossing lines formed by slow cooling inside an asteroid's core over millions of years. Today, it stands as one of the largest known meteorite sites on Earth, a silent reminder of the immense forces that occasionally visit from space and reshape our planet's surface. Fact 49. The Murchison meteorite and amino acids. On September 28, 1969, a fireball burst over the small town of Murchison, Australia, scattering fragments across farms and roads. But when scientists examined the recovered pieces, they realized they'd stumbled upon something extraordinary, a meteorite rich in amino acids. The Murchison meteorite, another carbonaceous chondrite, contains over 90 different amino acids, many of which are not found naturally on Earth. It also carries organic compounds like sugars and simple alcohols, suggesting that the chemistry of life may not be unique to our planet. What's fascinating is that these molecules formed in deep space, not inside a living organism, but through reactions within cold, dusty regions of the early solar system. The Murchison meteorite gave scientists a tangible clue that the ingredients for life may have been delivered to young Earth by falling space rocks. Each fragment of Murchison tells a story that connects the stars to the origins of biology, that the same cosmic dust that built the planets may also have sparked the chemistry that led to us. Fact 50. The Canyon Diablo meteorite and meteor crater. Near the desert town of Winslow, Arizona, lies a massive bowl-shaped depression, Meteor Crater, one of the best preserved impact sites on Earth. For years, people thought it was a volcanic feature, until scientists connected it to fragments of an ancient iron meteorite known as Canyon Diablo. About 50,000 years ago, a large iron-nickel meteorite travelling at tens of thousands of kilometers per hour slammed into the desert. The explosion released energy equivalent to several megatons of TNT, vaporizing most of the impactor and hurling debris miles away. The surviving pieces of the Canyon Diablo meteorite helped confirm that the crater was formed by a high-velocity cosmic impact, a key discovery that changed how geologists understood craters across the solar system. Meteor Crater stands today as both a natural wonder and a classroom from space, Every shard of Canyon Diablo iron that researchers hold tells the same story. When something from beyond Earth strikes with cosmic speed, it leaves behind not just destruction, but a lasting mark in the story of our planet. Fact 51. What defines an impact crater? Imagine standing in a wide, circular basin surrounded by walls of broken rock, a landscape that looks as if it has been punched by the universe itself. That's what an impact crater truly is, the scar left behind when a meteorite, asteroid, or comet strikes a planet's surface at incredible speed. Unlike volcanic craters, which form from eruptions, impact craters are explosions of energy. When a space rock hits, it releases kinetic energy that instantly vaporizes rock, melts minerals, and hurls debris in every direction. The result is a distinct bowl-shaped depression, often surrounded by raised rims and layers of ejecta, rock blasted outward by the collision. Small impacts form simple craters, but larger ones create complex structures with central peaks, terraces, and multi-ring basins. These shapes help scientists estimate the impact's size and force. Impact craters aren't just scars, they're time capsules. They reveal how often cosmic debris hits planets, how surfaces evolve, and even how life on Earth may have been influenced by catastrophic collisions. From tiny lunar pits to massive basins hundreds of kilometers wide, each crater tells a story written in stone, a record of the solar system's restless past. Fact 52. Barringer Meteor Crater, Arizona Drive east from Flagstaff, Arizona, and you'll find a site that looks almost too perfect to be natural. A massive round hole nearly a kilometer across and over 170 meters deep. This is Meteor Crater, also known as Barringer Crater, one of the most famous impact sites on Earth. About 50,000 years ago, an iron-nickel meteorite roughly 50 meters wide slammed into the Arizona desert at nearly 70,000 kilometers per hour. The explosion released energy equal to millions of tons of TNT. Most of the meteorite vaporized instantly, leaving behind a crater so well preserved that it remains nearly intact today. In the early 1900s, a mining engineer named Daniel Barringer became convinced the crater was formed by a meteorite impact, not a volcano, as many believed at the time. His research made him one of the first people to prove that impacts from space can shape our planet. Meteor Crater is now a natural laboratory, teaching scientists about both ancient and modern impacts. Standing on its rim, you can feel the vastness of the event, the moment when space quite literally met Earth with unimaginable force. Fact 53. The Chicxulub Crater, dinosaur extinction site. 66 million years ago, life on Earth changed forever. A 10-kilometer wide asteroid struck what is now the Yucatan Peninsula in Mexico, carving out the massive Chicxulub crater. The impact unleashed energy equivalent to billions of atomic bombs, vaporizing rock, igniting global wildfires, and throwing dust into the atmosphere that blocks sunlight for months. This event triggered one of the most famous mass extinctions in history, wiping out around 75% of species, including the non-avian dinosaurs. For years, the idea of an asteroid-caused extinction was just a theory, but in the 1990s, scientists discovered the buried rim of Chicxulub beneath layers of sediment, confirming the story. Drilling into the crater has revealed melt rock, shocked quartz, and chemical traces that all point to an impact of unimaginable power. The Chicxulub crater is not just a geological landmark, it's a turning point in Earth's biological history. A moment when devastation cleared the way for new life to evolve. Fact 54. The Vredefort Dome, largest known impact structure. In the heart of South Africa lies a vast circular formation stretching more than 300 kilometers across. This is the Vredefort Dome, the largest and oldest confirmed impact structure on Earth. It formed about 2 billion years ago, when a massive asteroid struck with enough energy to shake the entire planet. What's left today is the eroded core of that ancient crater, layers of rock bent and uplifted into a giant dome shape. The original crater may have been twice the size of the Chicxulub impact site, dwarfing nearly every other known structure of its kind. The force of the collision melted and reshaped the Earth's crust, exposing minerals that later fueled South Africa's rich mining regions. Scientists study Vredefort not only for its size but for what it teaches about the early Earth, a time when the planet's surface was constantly bombarded by massive impacts. Vredefort stands as a reminder that even the most stable continents carry deep scars from a violent cosmic past, scars that shape the world we live in today. Fact 55. Sudbury Basin in Canada. In Ontario, Canada, lies a vast oval-shaped depression surrounded by rugged hills. The Sudbury Basin, one of the largest and oldest impact structures on Earth, formed nearly 1.85 billion years ago. It was created when a giant asteroid slammed into the planet, releasing energy that reshaped the local landscape forever. The impact melted rock across hundreds of kilometers, creating a basin now rich in nickel, copper, and platinum group metals. Over time, tectonic forces and erosion distorted its shape, but deep beneath the surface, the structure still holds the unmistakable signature of a colossal impact. For decades, scientists debated whether Sudbury's strange geology came from volcanic activity or a meteorite. It wasn't until microscopic shocked minerals and melt sheets were discovered that its extraterrestrial origin was confirmed. Today, Sudbury isn't just a mining hub. It's a window into Earth's ancient bombardment history, a place where science and geology come together to reveal the lingering fingerprints of the universe's most powerful events. Fact 56. Manicouagan Crater in Quebec. In the wilderness of northern Quebec lies one of Earth's most striking geological features, a perfect ring filled with water, visible even from space. This is the Manicouagan Crater, a colossal reminder of a collision that took place around 214 million years ago. When a massive asteroid slammed into what was then a lush landscape, it released energy equivalent to millions of nuclear blasts. The explosion excavated a crater nearly 100 kilometers wide and melted the surrounding rock into a circular scar that still shapes the terrain today. Over time, glaciers carved into the impact site, and water filled its centre, forming the beautiful Manicouagan Reservoir, often called the Eye of Quebec. The central island, René Levasseur Island, marks the rebound peak, the spot where the crust rebounded upward after the impact. Scientists study Manicouagan to understand not only the power of ancient impacts, but also their global effects. Some even suggest this event may have influenced the environmental shifts that led to one of the smaller mass extinctions in the Triassic period. Today, it stands as both a natural wonder and a geological memory, the Earth's landscape forever reshaped by a visitor from the sky. Fact 57. Lona Crater in India. In the heart of Maharashtra, India, lies Lona Crater, a nearly circular basin with a mysterious green lake at its centre. For centuries, locals wondered how it formed. Myths and legends surrounded it, until scientists revealed its true origin: a meteorite impact about 50,000 years ago. What makes Lona so fascinating is its setting. Unlike most craters, which form in sedimentary rock, Lona struck basalt, the same kind of volcanic rock found on the Moon and Mars. That makes it an ideal natural laboratory for studying extraterrestrial geology right here on Earth. The crater is about 2 kilometers wide and over 100 meters deep. Its lake water is both salty and alkaline, hosting unique microbial life adapted to its extreme chemistry. Over time, plants, animals, and bacteria have turned this alien-looking site into a living ecosystem. Lona Crater reminds us that cosmic violence and biological life can coexist. Out of destruction came something astonishing, a lake that became a world of its own, shaped by an ancient explosion from beyond Earth. Fact 58. Tunguska Explosion. Mystery of 1900 rate, just after dawn on June 30th, 1908. A blinding fireball raced across the sky over Siberia and then exploded. The blast flattened more than 2,000 square kilometers of forest near the Tunguska River, knocking down 80 million trees. The strange part, there was no crater. When explorers reached the site years later, they found scorched trees but no trace of an impactor. The explosion had occurred several kilometers above the ground, likely caused by an asteroid or comet fragment about 50 meters wide that disintegrated mid-air. The Tunguska event remains one of the most powerful explosions in modern history, releasing energy comparable to thousands of atomic bombs. Witnesses hundreds of kilometers away saw the sky glowing for days afterward. For decades, scientists have studied Tunguska to understand the dangers of airbursts when space rocks explode before hitting the ground. Though it left no crater, Tunguska stands as one of Earth's greatest cosmic mysteries and a reminder of how fragile our world can be under the sky's silent watch. Fact 59. How impact craters shape planetary history. If you look at the moon through a telescope, you'll see it, a surface covered in craters. Those same circular scars exist on every rocky world in our solar system, including Earth. Each one tells a story of impact and transformation. Impact craters shape planetary history in countless ways. On early Earth, massive collisions delivered water and organic materials, possibly influencing the conditions that allowed life to begin. Later, smaller impacts shaped landscapes, created basins, and triggered climatic changes. When a large asteroid hits, it reshapes the crust, exposes deep materials, and sometimes even alters the planet's atmosphere. The evidence can last for billions of years, recording a timeline of cosmic encounters. On other worlds, like Mars, Mercury, and the Moon, craters help scientists estimate age. Surfaces with more craters are older. Those with fewer are geologically younger. It's like reading wrinkles on a planet's face. Impact craters are more than scars. They're historical records of the solar system's evolution, revealing how violence and creation have always existed side by side. Fact 60. Crater lakes and their ecosystems. Sometimes, what begins as destruction ends in beauty. Over time, many impact craters fill with rainwater, snowmelt, or groundwater, becoming serene crater lakes. These lakes, born from cosmic collisions, often evolve into thriving ecosystems teeming with life. Examples stretch across the globe, from Lona Lake in India to Lake Bosumtwi in Ghana and Lake Manicouagan in Canada. Each has its own balance of minerals, microbes, and aquatic plants, shaped by the chemistry of the surrounding rock. Because crater basins are often isolated, they act as natural laboratories for studying evolution, climate change, and even astrobiology. Some scientists believe that similar impact basins on Mars might once have held water, and perhaps even microbial life. Crater lakes also hold cultural and environmental significance. They provide fresh water, support biodiversity, and sometimes become sacred or protected sites. In the end, crater lakes remind us that the universe's most violent events can create calm and beauty on Earth, life blooming quietly in the shadows of ancient destruction. Fact 61. How impact shaped early Earth. Long before mountains rose or oceans formed, Earth was a wild and molten world, constantly battered by space debris. During its earliest era, billions of years ago, asteroid and comet impacts shaped the planet's surface in ways we can still trace today. These collisions were unimaginably powerful. Some melted entire regions of the crust. Others delivered the ingredients that helped Earth evolve into a habitable world. With each strike, the planet's surface cooled, mixed, and transformed. Over time, the chaos gave way to stability. Continents began to form, and the first oceans likely filled the scars left behind by giant impacts. Impacts didn't just scar the Earth, they helped build it. By delivering metals like iron and nickel, they contributed to the planet's core composition. Some impacts may even have helped stabilize Earth's spin or tilt, creating conditions that allowed climates to balance and life to eventually emerge. It's hard to imagine, but without those early bombardments, the Earth we know, blue, stable and alive, might never have taken shape. The violence of space was, in many ways, the sculptor of our home. Fact 62. The Late Heavy Bombardment. Around 4 billion years ago, the inner solar system went through a violent phase known as the Late Heavy Bombardment, a time when asteroids and comets bombarded the young planets, carving out craters that still scar the Moon and Mars today. Scientists think this event happened when the orbits of the giant planets, Jupiter, Saturn, Uranus and Neptune, shifted, disturbing the asteroid belt and sending a cascade of debris inward toward Earth and its neighbours. For hundreds of millions of years, our planet was hit again and again by objects large enough to boil oceans and vaporise rock. The surface may have been repeatedly melted, sterilising it of early life, or paradoxically creating conditions that made life possible. By delivering heat, minerals and volatile elements like carbon and nitrogen, these impacts helped lay the foundation for Earth's chemistry and crust. The Moon's cratered surface is a snapshot of that chaotic time, a record of the cosmic storm our planet endured. The Late Heavy Bombardment reminds us that creation often begins in destruction. The same impacts that once made Earth inhospitable may have prepared it for life. Fact 63. The role of meteorites in bringing water. One of the great mysteries in planetary science is where Earth's water came from. The early planet was far too hot for liquid water to exist. Yet today, our oceans cover more than 70% of the surface. The answer, scientists believe, may lie in meteorites and comets. Some meteorites, especially carbonaceous chondrites, contain minerals with water locked inside their structure. Ancient ice and hydrated compounds preserved since the solar system's birth. When these space rocks bombarded early Earth, they may have released that water as vapour, which later condensed to form oceans and rivers. Studies comparing hydrogen isotopes in meteorites and seawater show striking similarities, suggesting that much of our water truly came from the sky. Comets likely contributed too, delivering frozen water and other volatile compounds. Every drop of rain, every wave, every glacier might trace its origin back to countless impacts from space. The same celestial collisions that once seemed catastrophic may have filled our planet with the element that made life possible. Fact 64. Could life's building blocks have come from space? If water came from the sky, what about life itself? Or at least its ingredients? Scientists have long wondered whether life's building blocks might have arrived on meteorites and comets billions of years ago. We know that some meteorites, like the Murchison and Tagish Lake Falls, contain amino acids, sugars, and organic compounds, the same molecules found in living organisms. These substances can form naturally in the cold, radiation-filled clouds of interstellar space, and then hitch a ride on asteroids. When these rocks crashed into early Earth, they may have delivered those molecules to warm ponds and oceans, where chemistry took over, eventually leading to the first self-replicating systems. This idea, called panspermia, doesn't claim life itself came fully formed from space, but that the raw materials, carbon, hydrogen, nitrogen and organic molecules, arrived from beyond our world. It's poetic to think that everything alive today may carry traces of an ancient cosmic recipe, sprinkled onto a young Earth by falling stars. Fact 65. Major extinction events from impacts. Throughout Earth's history, life has flourished, and then suddenly vanished, in cycles of creation and loss. Some of the most devastating mass extinctions were triggered not by slow climate shifts or volcanic eruptions, but by cosmic impacts. The most famous is the Chicxulub impact 66 million years ago, which wiped out the non-avian dinosaurs. The blast sent dust and sulfur into the atmosphere, blocking sunlight and collapsing food chains worldwide. But it wasn't the only one. Earlier events, such as the possible impact at the end of the Permian period, may have contributed to even greater losses of species. These catastrophes reshaped evolution itself, clearing ecosystems and allowing new life forms to emerge in their wake. Impacts are nature's reset button, sudden, uncontrollable, and transformative. They remind us that life on Earth is both fragile and resilient, always adapting to the rhythms of the cosmos. The same sky that gives us light and wonder can, in a single instant, change the course of life forever. Fact 66. The KT extinction and evidence of iridium. 66 million years ago, a moment of unimaginable violence changed life on Earth forever. A massive asteroid slammed into what is now the Yucatan Peninsula, carving out the Chicxulub crater and ending the reign of the dinosaurs. This event, known as the Cretaceous-Tertiary (KT) extinction, wiped out about 75% of all species on Earth. The smoking gun for this catastrophe came from an unexpected clue: iridium. This rare metal is scarce in Earth's crust but common in asteroids. In the late 1970s, scientists Lewis and Walter Alvarez discovered a thin global layer of clay rich in iridium, marking the exact boundary between the Cretaceous and Tertiary periods. This discovery revolutionized science, proving that an extraterrestrial impact could alter the course of evolution. The iridium layer is now one of the most compelling pieces of evidence that space rocks have shaped life's destiny on our planet. Fact 67. Earth's hidden craters. Under ice and ocean. Many of Earth's largest impact scars remain invisible, buried beneath glaciers, sediments, or the sea. Because erosion and plate tectonics constantly reshape our planet, only a fraction of its true impact history is visible on land. Some enormous craters lie hidden beneath the ocean floor, detected only by satellite data and gravity mapping. Others are buried under ice, like the Hiawatha crater in Greenland, discovered beneath nearly a kilometre of ice and possibly linked to a late Ice Age event. These concealed craters remind scientists that Earth's story is incomplete, that many of its cosmic collisions are still hidden from sight, waiting to be uncovered. Each new discovery helps piece together the long, violent relationship between Earth and the cosmos. Fact 68. Recent near misses with Earth. Even today, Earth is not immune to the dangers of space. Every year, small asteroids and near-Earth objects, NEOs, pass alarmingly close to our planet, some even closer than the Moon. In 2013, the Chelyabinsk meteor exploded over Russia with the force of several nuclear bombs, injuring over 1,000 people. Just hours later, another asteroid, 2012 DA14, passed within 27,000 kilometers of Earth, inside the orbit of some satellites. Astronomers constantly track thousands of NEOs to ensure early warning of potential collisions. These near misses remind us that Earth lives in a cosmic shooting gallery, where luck and vigilance often stand between us and disaster. Fact 69. Frequency of catastrophic impacts. How often do planet-changing impacts happen? Fortunately, truly catastrophic collisions are rare, but not impossible. Small meteors strike Earth daily, burning up harmlessly in the atmosphere. Larger impacts like Chelyabinsk occur every few decades. Asteroids big enough to destroy cities hit roughly every few thousand years, while global-scale impacts like Chicxulub are thought to occur once every 100 million years or so. Still, the odds never fall to zero. That's why scientists worldwide monitor asteroid paths and develop planetary defense strategies, including proposed missions to deflect dangerous objects before they strike. The history of our planet shows that impact events are inevitable. The challenge is ensuring we're ready when the next one comes. Fact 70. What small impacts teach us about big ones. Every fireball that streaks across the night sky is a small-scale experiment in planetary science. By studying minor impacts and meteor falls, scientists learn how larger, more destructive events unfold. Tiny impacts reveal how energy dissipates, how shock waves travel, and how minerals transform under extreme pressure. Laboratory simulations of micrometeorite strikes help model what happens when asteroids collide with planets, from crater formation to atmospheric effects. Even small craters, like Arizona's Barringer crater, serve as natural laboratories, showing how a single impact can release more energy than a nuclear explosion. Each fragment, streak, and crater, no matter how small, tells a story about cosmic energy, planetary evolution, and the thin line that separates everyday events from global catastrophe. Fact 71. How astronomers detect incoming objects. Imagine staring into the night sky, knowing that somewhere out there, a rock the size of a mountain could be on a collision course with Earth, and you might be the first person to spot it. That's the daily reality for astronomers who scan the heavens for incoming objects. They use wide-field telescopes equipped with automated cameras and software that track anything moving against the backdrop of distant stars. If a tiny dot shifts position night after night, it could be a new asteroid or comet. Once found, its orbit is calculated using precise measurements of its movement, revealing whether it poses any threat. Some of the most powerful survey programs, like Pan-STARRS in Hawaii and Catalina Sky Survey in Arizona, have discovered thousands of near-Earth asteroids. These modern sky watchers are our early warning system, constantly searching for anything that might come too close for comfort. Fact 72. NASA's planetary defense programs. It sounds like something out of a science fiction movie, but planetary defense is a very real branch of science. NASA leads the effort to detect, track, and, if necessary, deflect hazardous asteroids before they hit Earth. At the center of this mission is NASA's Planetary Defense Coordination Office, PDCO. Its job is to oversee all asteroid detection networks, evaluate threats, and coordinate global responses. One of its biggest achievements was the DART mission, Double Asteroid Redirection Test, in 2022, where a spacecraft intentionally crashed into an asteroid called Dimorphos, successfully changing its orbit. That single experiment proved humanity could alter the path of an asteroid, a small but monumental step toward protecting our planet from future impacts. Fact 73. The role of telescopes and radar tracking. Telescopes catch the first glimpses of asteroids, but radar tracking provides the details that really matter: their size, shape, rotation, and exact trajectory. Once an object is discovered, powerful radar systems like those at NASA's Goldstone Observatory in California and Arecibo, before its collapse, send radio waves that bounce off the asteroid's surface. The echoes return data that's incredibly precise, accurate enough to predict an asteroid's position decades into the future. Combined with optical observations from telescopes, radar helps scientists refine impact predictions and even map the rugged surfaces of asteroids millions of kilometers away. It's a partnership of light and radio that turns distant, silent rocks into well-understood neighbours in space. Fact 74. Near-Earth objects, NEOs. Explained near-Earth objects, or NEOs, are asteroids and comets whose orbits bring them within about 50 million kilometres of Earth's path. Most are harmless, but a few come close enough to make astronomers sweat a little. NEOs are classified based on how their orbits cross Earth's Arcturus, Amos, Apollos, and Eteans, each following a slightly different route around the Sun. Some are as small as pebbles, others could span kilometres. Tracking them isn't just about safety. NEOs are also time capsules from the early solar system, containing unaltered material from billions of years ago. By studying them, scientists gain clues about how planets formed, and maybe even how the ingredients for life arrived here. Fact 75. How scientists predict impact probabilities. Once an asteroid is spotted, astronomers race to calculate its orbit and impact probability, essentially the odds that it might hit Earth. These calculations depend on dozens of observations over time, measuring how sunlight, gravity, and other forces nudge the asteroid's path. Specialized systems like NASA's Sentry and the European NEODIS constantly update risk assessments. They can predict possible future impacts decades, even centuries, ahead. Most objects quickly drop to zero risk as more data refines their orbits, but some remain under close watch. The math behind it is mind-bending, yet the goal is simple: to know early, to prepare wisely, and to ensure that the next big rock from space becomes a story of prevention, not survival. Fact 76. The Torino scale for impact hazards. When scientists talk about asteroid threats, they need a simple way to explain how dangerous a potential impact really is. That's where the Torino scale comes in, a colour-coded warning system that ranks potential impact events from 0 to 10. A score of 0 means there's no risk at all. The asteroid poses no danger. 1 might mean a routine near-Earth pass. As you move up the scale, the colours change from green to yellow, orange, and finally red, where 10 represents a catastrophic collision capable of global destruction. Most newly discovered asteroids start with a low rating, and as astronomers refine their data, the risk usually drops to 0. But every now and then, something pops up in the yellow zone, and the world briefly holds its breath until new observations bring relief. It's a simple yet powerful way to translate complex orbital data into something everyone can understand. A universal language of cosmic risk. Fact 77. Space missions. That study asteroids, like OSIRIS-REx. If meteorites are messengers from space, then asteroid missions are the expeditions sent to meet the messengers' families. One of the most groundbreaking examples is NASA's OSIRIS-REx mission, launched in 2016 to visit the near-Earth asteroid Bennu. The spacecraft spent years orbiting and studying Bennu up close, mapping every rock and crater before finally touching down to collect samples. In 2023, its sample capsule parachuted back to Earth, carrying bits of pristine asteroid material, untouched since the dawn of the solar system. Other missions have done similar work. Japan's Hayabusa and Hayabusa Doom brought back samples from asteroids Itokawa and Ryugu. These missions help scientists understand the composition of asteroids, their potential resources, and their behavior if one ever needed to be deflected. Each mission is like a time machine, bringing home pieces of our solar system's earliest days. Fact 78. How scientists recover fresh meteorites. When a meteorite falls, time is everything. Within hours, weather and contamination can alter or destroy key evidence. That's why scientists rush to recover fresh falls as quickly as possible. Using eyewitness reports, video footage, and radar data, teams triangulate where the meteor likely landed, an area called the strewn field. Then begins the search, walking carefully across deserts, snowfields, or farmlands, scanning for small blackened stones that don't quite match their surroundings. If found early, these samples can reveal organic compounds, isotopic ratios, and fragile minerals that would vanish with exposure. Recovering a fresh meteorite is like catching a message from space before it fades, a race between science and time. Fact 79. Meteorite hunting techniques. Not all meteorites are found right after they fall. Many lie unnoticed for centuries, waiting for sharp eyes and patient hunters. The best hunting grounds are deserts and ice fields, places where dark stones stand out against pale backgrounds and erosion is slow. In Antarctica, scientists search the blue ice for meteorites that have migrated upward through the moving ice sheet. In hot deserts like the Sahara or Atacama, hunters use metal detectors and magnets, since most meteorites contain iron and nickel. Each find is catalogued, studied, and stored in laboratories, not for their value as collectibles, but for the stories they tell about our solar system's past. Every stone, no matter how small, is a clue from beyond the sky. Fact 80. Using satellite and video data to trace meteor paths. When a fireball streaks across the night sky, satellites and cameras around the world silently capture the show. These recordings have become one of the most powerful tools for tracing meteor paths and predicting where fragments might land. Weather satellites detect flashes of light from space, while networks like NASA's All-Sky Fireball network use wide-angle cameras to triangulate exact trajectories. Even security cameras and dashboard videos from ordinary people can help scientists reconstruct a meteor's final moments, as famously happened with the Chelyabinsk event in 2013. By analysing angles, timing and brightness, researchers can pinpoint where a meteor came from and where it likely fell. It's a mix of astronomy, geometry, and detective work, turning fleeting streaks of light into hard scientific evidence. Fact 81. Ancient worship of stones from the sky. Long before telescopes or satellites, people looked up at the night sky and saw mystery. Fireballs blazing across the heavens, stones seemingly falling from nowhere. To ancient cultures, these stones from the sky weren't just rocks. They were sacred gifts from the cosmos. In many parts of the world, meteorites were treated with reverence. Some were placed in temples, others became symbols of divine power or celestial connection. In ancient Greece and Rome, these strange stones were often enshrined and worshipped. Across Asia and the Middle East, too, such objects were viewed as omens, messengers from beyond the world of men. Without science to explain them, meteorites felt supernatural, tangible proof that the heavens could touch the earth. It's remarkable how a simple piece of cosmic iron could stir such awe that entire legends were built around it. Fact 82. Meteorite iron in ancient weapons and jewellery. Long before humans learned to smelt iron from ore, some of the first metal tools ever made were crafted from meteorites. The reason? Meteorite iron is rich in nickel and nearly pure, ready for shaping once discovered. Archaeologists have found ancient knives, beads and ornaments made from this cosmic metal in Egypt, Turkey and China, all dating back thousands of years, long before the Iron Age officially began. These artifacts often carry a unique crystalline pattern, called the Widmanstätten structure, which forms only in metal cooled slowly inside asteroids over millions of years. For ancient people, working such rare metal wasn't just craftsmanship. It was artistry born from the stars. Every strike of a hammer was, in a sense, forging the cosmos into human history. Fact 83. Tutankhamun's meteoric dagger. One of the most famous examples of meteoritic metal lies in the tomb of Pharaoh Tutankhamun. Discovered in the 1920s, the young ruler's burial treasures included a dagger that puzzled researchers for decades. Its blade was iron, yet forged centuries before Egypt's Iron Age. In 2016, scientists used X-ray fluorescence to solve the mystery. The dagger's composition contained a high percentage of nickel and cobalt, matching meteorite metal. In other words, Tutankhamun's dagger was forged from a fallen star. It's an astonishing reminder that long before people understood space, they were already shaping fragments of it, carrying pieces of the universe into their daily lives and burial rituals. Fact 84. The Kaaba's Black Stone. A possible meteorite origin. At the heart of Mecca stands the Kaaba, the most sacred site in Islam. Embedded in one corner of the Kaaba is the Black Stone, a revered object venerated for centuries. While its exact composition remains a matter of faith and tradition, some scholars and geologists have speculated that it might be a meteorite or impact glass. There's no definitive proof, and the stone has undergone centuries of handling, damage and restoration. Still, the idea that it could be a relic from the sky captures something deeply human, our instinct to connect what falls from above with what we hold sacred below. Whether celestial or terrestrial, the Black Stone reflects a universal truth. Across cultures and time, humanity has always sought meaning in the sky's most mysterious gifts. Fact 85. Myths and folklore about falling stars. Before science gave us the word meteor, falling stars filled the world's imagination. In folklore, they were omens of change, sometimes luck, sometimes disaster. In Europe, people whispered that wishing upon a falling star would make dreams come true. In Japan, Meteors were thought to carry the souls of ancestors. In Polynesia, fiery streaks were signs from the spirit world, while in parts of Africa, they foretold births, deaths, or the fate of kings. Every culture saw something different in that brief flash of light, but the feeling was always the same: wonder, fear, and awe at the universe beyond our reach. Even now, when we watch a meteor streak through the night, there's still that ancient instinct to make a wish, as if, deep down, we remember when people believed the stars were speaking to us. Fact 86. Meteorites in art and literature. From the moment people realized stones could fall from the sky, meteorites began to capture the imagination of artists and writers alike. These fragments of space weren't just scientific curiosities, they were symbols of mystery, fate, and wonder. In classical times, poets wrote about heavenly stones as messengers between worlds. Centuries later, meteorites inspired romantic painters and novelists who saw them as emblems of the unknown. The 19th century brought tales of cosmic catastrophes and interplanetary travel, with authors like Jules Verne and H.G. Wells using meteorites as symbols of discovery or destruction. In modern art, some creators even incorporate real meteorite fragments into their sculptures or jewellery, blending science and creativity in tangible form. There's something poetic about it, turning ancient pieces of the universe into works of human imagination. After all, nothing connects art and science more beautifully than a stone that has travelled through both space and time. Fact 87. Early scientific studies of meteorites. Before meteorites were understood as space rocks, their very existence puzzled scientists. For centuries, people dismissed eyewitness accounts of stones falling from the sky as superstition. Yet a few curious minds began to wonder, what if they were real? In the 18th century, a handful of natural philosophers started collecting strange metallic rocks that didn't fit local geology. They noted unusual characteristics: high iron content, magnetic pull, fusion crusts. But without proof of their celestial origin, skepticism prevailed. It wasn't until the late 1700s that scientists like Ernst Chladni, a German physicist, began arguing that these stones were extraterrestrial. In 1794, he published a paper suggesting meteorites came from space, not volcanoes or storms. People laughed, but history would prove him right. Chladni's persistence opened the door to a new field of study: meteoritics, the science of rocks from beyond Earth. Fact 88. How skepticism about meteorites ended in the 19th century. For centuries, even educated minds refused to believe stones could fall from the sky. That changed dramatically in April 1803, when a shower of thousands of meteorites fell over l'Aigle, France. The event caused an uproar. Eyewitnesses described thunder-like explosions and raining stones. The French Academy of Sciences sent investigator Jean-Baptiste Biot, who collected samples, mapped the fall area, and analysed the rocks. His report was undeniable. These stones were not from Earth. That single event turned skepticism into acceptance almost overnight. Meteorites were finally recognised as cosmic visitors, not local oddities. It marked the birth of modern meteorite science and shifted our understanding of Earth's connection to space forever. Fact 89. Meteorites in museums around the world. Walk into a great museum in London, New York, Paris, or Tokyo, and you'll likely find a meteorite display that stops you in your tracks. These dark, heavy stones rest quietly in glass cases, yet each one carries the weight of billions of years of history. The Natural History Museum in London houses the Canyon Diablo meteorite from Arizona's Meteor Crater. The Smithsonian Institution displays the enormous Cape York meteorite, which once served as an iron source for Arctic peoples. In Vienna, the Naturhistorisches Museum holds one of the largest meteorite collections in the world. Visitors often linger, staring at these unassuming stones, realizing they're looking at fragments of other worlds, pieces of Mars, the Moon, or the asteroid belt. Museums keep them not just for study, but as reminders of how small and yet how connected we are to the wider universe. Fact 90. Modern collectors and the meteorite market. Today, meteorites aren't just scientific treasures, they've become coveted collectors' items. Private collectors, universities, and enthusiasts around the world hunt for these rare fragments, sometimes paying thousands of dollars per gram, depending on rarity and origin. A piece from Mars or the Moon can fetch astonishing prices, while common chondrites remain affordable to amateur collectors. Online markets and specialized auctions now trade verified specimens, often accompanied by documentation and classification reports. While commercialization can raise concerns about scientific loss, it has also sparked global interest in planetary science. Many collectors collaborate with researchers, donating significant finds for study. In a way, the meteorite market reflects humanity's enduring fascination, not with wealth, but with owning a small, physical piece of the cosmos. It's a reminder that even in the modern age, the magic of stones from the sky hasn't faded, it's simply taken on a new form. Fact 91. How meteorite studies help plan space missions. When spacecraft venture toward asteroids or other planets, the knowledge guiding those missions often comes from a surprising source: meteorites found on Earth. Every meteorite is a physical sample of space, a preview of what robotic explorers might encounter millions of kilometers away. By studying their chemistry, texture, and mineral makeup, scientists learn how to build instruments, design drills, and choose landing sites. For instance, what we know about asteroid Bennu's surface helped shape NASA's OSIRIS-REx mission. And that understanding came from years of studying similar meteorites in laboratories. These space rocks reveal how dust, ice, and metals behave in microgravity, crucial for both landings and sample collection. In a sense, meteorites act as training material for future missions. Each fragment studied on Earth brings space a little closer and helps engineers prepare for the real thing. Fact 92. What meteorites reveal about asteroid mining potential. The idea of mining asteroids might sound futuristic, but meteorites have already shown us what riches await out there. Many meteorites, especially iron and stony iron types, contain valuable metals such as nickel, cobalt, and platinum group elements. These are the same materials we use in electronics, batteries, and high-tech manufacturing on Earth. By analyzing meteorites, scientists can estimate the composition of asteroids and determine which types are worth mining. Some are rich in water ice, a potential resource for fuel production in space, while others are packed with metals that could support off-world construction. In a way, every meteorite that falls to Earth is a free sample of an asteroid mining prospect. They tell us what's out there, what's valuable, and how those materials formed. All vital clues for a future where humanity might not just visit asteroids but work among them. Fact 93. Understanding planetary cores through iron meteorites. Deep beneath every planet lies a core, dense, metallic, and hidden from direct observation. Since we can't drill thousands of kilometers down, scientists turn to iron meteorites for answers. These metallic visitors are believed to come from the shattered cores of ancient planetesimals, the small worlds that existed before the planets we know today fully formed. Their crystal structures, cooling rates, and chemical signatures reveal what happens inside molten cores as they solidify over millions of years. By examining them, scientists gain insight into Earth's own inner structure, the pressures, temperatures, and magnetic processes shaping our planet's heart. Each iron meteorite is a tiny laboratory of planetary evolution, preserving secrets from the earliest days of solar system formation. Fact 94. Meteorites and the search for extraterrestrial life. When scientists search for life beyond Earth, meteorites offer some of the most compelling evidence. Not proof, but clues that life's ingredients are widespread in the universe. Certain carbon-rich meteorites, like the Murchison and Tegish Lake Falls, contain amino acids, hydrocarbons, and complex organic molecules, the same building blocks found in living things. While these compounds didn't form life themselves, they show that chemistry capable of leading to life happens naturally in space. This discovery fuels theories that life's raw materials were delivered to early Earth through meteorite impacts, seeding the planet with the ingredients for biology. Each new analysis strengthens the idea that we might not be alone, that similar chemical beginnings could be unfolding on countless other worlds. Fact 95. Using isotopes to date the solar system. One of the most remarkable things scientists can do with meteorites is measure time itself. Not human time, but cosmic time stretching back billions of years. They do this through isotopic dating, a technique that analyzes the decay of radioactive elements within meteorite minerals. By measuring ratios of isotopes such as uranium-lead or rubidium-strontium, researchers can determine when those minerals crystallized, effectively revealing the age of the solar system. Many meteorites date back about 4.5 billion years, older than any rock on Earth's surface. These isotopic fingerprints act like timestamps frozen in stone, marking the earliest moments when dust and gas first condensed into solid worlds. In a way, every meteorite is a cosmic clock, silent, ancient, and still ticking from the dawn of our planetary story. Fact 96. Simulating impacts in laboratories. To understand what happens when a meteor strikes a planet, scientists recreate those violent moments on a much smaller scale. In special laboratories, they use high-velocity guns, lasers, and shock chambers to fire tiny projectiles at target materials, mimicking the immense speeds and pressures of real cosmic impacts. These experiments reveal how craters form, how rocks melt or vaporize, and what kind of shock patterns remain inside minerals. By comparing lab results with actual meteorites and craters, researchers can reverse engineer ancient events, piecing together details like impact angle, speed, and energy. In essence, these controlled collisions let us replay the drama of planetary history, one micro-explosion at a time, to understand how impacts have shaped worlds across the solar system. Fact 97. How meteorites are preserved and studied today. Once a meteorite is found, the real work begins. Scientists carefully preserve these extraterrestrial samples to prevent contamination from Earth's air, moisture, or microbes. Clean labs store them in nitrogen-filled cabinets, and researchers use gloves, special tools, and microscopes to handle them. Modern techniques like scanning electron microscopy, X-ray diffraction, and mass spectrometry allow scientists to study a meteorite's structure atom by atom. Every detail, from its minerals to trapped gas bubbles, tells a story about where it came from and what it's been through. Preserving meteorites isn't just about science, it's about protecting pieces of the early solar system. Each rock holds clues that can never be replaced, so their care is as meticulous as handling ancient relics of cosmic history. Fact 98. Protecting Earth from future impacts. While meteor strikes are rare, the danger is real, and humanity is finally learning how to defend itself. Agencies like NASA's Planetary Defense Coordination Office track thousands of near-Earth objects, NEOs, and develop strategies to deflect or destroy any that might threaten our planet. In 2022, NASA's DART mission made history by deliberately crashing a spacecraft into an asteroid to change its orbit, the first real-world test of asteroid deflection. The success proved that humans can alter the path of a celestial body, giving us a vital tool for planetary protection. With better telescopes, early warning systems, and international cooperation, Earth's defense network grows stronger each year. The goal is simple: to make sure the next big impact remains only a scientific curiosity, not a global catastrophe. Fact 9. The possibility of future extinction-level impacts. Although civilization is far more advanced than in the age of the dinosaurs, Earth is still exposed to the same cosmic risks. Large asteroids or comets, even a few kilometers wide, could cause devastating effects if they struck today, triggering firestorms, global cooling, and mass extinction. Fortunately, events of that scale are extremely rare, occurring over tens of millions of years. Still, studying past impacts like Chicxulub reminds scientists that such threats are part of our planet's natural cycle. By modelling orbital paths and simulating outcomes, researchers estimate probabilities and prepare emergency plans. The message from science is clear. We can't stop cosmic impacts from existing, but we can understand and prepare for them, and that understanding may one day save life on Earth. Fact 100. What meteorites teach us about our cosmic origins. In the end, meteorites are more than falling rocks. They're messengers from the dawn of creation. Inside them are minerals older than Earth itself, dust from ancient stars, and the same elements that make up our bodies. By studying them, we trace our lineage not just to Earth, but to the cosmos. Meteorites reveal how planets formed, how water and organic compounds arrived here, and how everything we know began in the heart of long-dead stars. Every fragment that lands on Earth is a chapter from our universal story, written in stone and delivered across light years. Through them, we glimpse where we came from, and perhaps where we are destined to go.